Hi everyone, I'm Inbal and I'm here to present our joint work on avoiding post-processing with context, texture boundary detection in metallography. We focused on improving the detection of texture boundaries in metallographic images, an area crucial for material science and its applications. Our goal is to enhance boundary detection within metallographic textures to improve our understanding of microscopic material properties. Automated texture analysis is critical in material science, providing precise insights that are essential for evaluating and optimizing material performance. One of our key goals is to approximate grain boundaries in metallography accurately, which is challenging due to the intricate nature of texture boundaries. A main challenge in metallography is accurately defining boundaries within complex texture-rich images. Traditional segmentation models often struggle with these images due to the lack of clear object boundaries, making standard techniques less effective. Current state-of-the-art segmentation models like the Segment Anything model are not optimized for pure texture images. They rely on predefined prompts and object-based features which are absent in metallographic images. As shown here, Segment Anything fails to segment texture boundaries effectively, highlighting the need for a method specifically tailored to texture detection. We used the texture boundary in metallography TBM dataset as a benchmark for our research. This dataset is as general as possible with annotations that correspond to the task of texture boundary detection in microscopy and especially in metallography. MLOgraphy was an earlier method for detecting grain boundaries in metallographic images using 128 squared fully annotated patches with a unit model. However, its reliance on small localized annotations limited its ability to adapt to a broader contextual variation. As shown here, the results required extensive post-processing, including binarization and watershed contouring, to produce complete boundary maps. This dependency increased the risk of overfitting and limited the model's ability to generalize to new textures. We present MLOgraphy++, an improvement upon MLOgraphy that uses larger partially annotated context windows. By applying a loss only on annotated areas while preserving the background context, this approach significantly reduces the need for post-processing. Clemex Studio is a no-code platform for developing semantic segmentation algorithms using partial annotations. It was used to train the MLOgraphy++ model. The platform offers a streamlined workflow, allowing users to upload images, annotate them, and train segmentation algorithms based on partial annotations. In here we see an image from the TBM dataset with partial annotations added in the Clemex Studio system. This semi-click segmentation method is used to label the grains, providing context for further segmentation training. Here you can see the results from Clemex Studio after training is complete. The predicted grain boundaries are shown on the right, demonstrating the effectiveness of the model after iterative refinement with partial annotations. The Heyn intercept method is a classical technique for measuring average grain size by counting intercepts along systematically placed test lines. While widely used, it has limitations. It assumes clear, fully visible boundaries, struggles with irregular or incomplete ones, and is sensitive to line placement, which can lead to underestimations of ambiguous or fragmented grains. Here, the classical Heyn intercept method is applied to a sample image. The figure shows grain size measurements representing intercept counts along test line and the average grain size. We use a variation of the Heyn intercept method called the Heyn compare, which calculates average distances between intercepts along fixed lines. This approach improves accuracy for irregular and partial boundaries, reducing reliance on fully closed contours in real-world images. In here you can see the Heyn compare method applied to a cropped image from the TBM dataset using horizontal lines to measure the grain boundaries. These graphs show the grain size distributions for the individual samples using the Heyn compare method. They highlight how MLOgraphy++ closely matches MLOgraphy and the ground truth, all without requiring post-processing. For future work, we aim to address the limitations of current datasets by expanding coverage to include diverse metallographic images and fine-tuning transformer-based models like SEM to handle complex segmentation challenges in metallography. We fine-tuned AutoSEM similar to the MLOgraphy method to explore its potential for future work. AutoSEM replaces manual prompts in SEM with an automated encoder for fully automated segmentation. It was trained on 256 squared fully annotated TBM crops for 100 epochs with augmentations and post-processing. AutoSem demonstrates effective segmentation of intricate grain boundaries, closely aligning grain size predictions with ground truth. While IOU and dice metrics were low due to complex structures, the Heyn compare method highlights its reliability. These promising results show the potential of fine-tuning SEM for metallographic segmentation, which we plan to further explore in our future work. Thank you for listening.